A knight's armor was no match for the edge of these ancient swords. I am talking about legendary blades like the Viking Ulfbert and the Middle Eastern Damascus Steel, weapons whose secrets have baffled experts for centuries. By the end of this, you will understand how medieval blacksmiths accidentally built nanotechnology into their steel, a feat our best labs still cannot copy. What did these masters know that we have forgotten, and what invisible architecture hides within the metal? How does this discovery force us to rewrite everything we thought we knew about technological progress? When you hear the term Dark Ages, what does it truly bring to mind? The warrior's hand tightens around the hilt, the blade catching the light not with a dull gray sheen, but with a silvery, almost liquid shimmer. This was no ordinary weapon. Forged between the 8th and 11th centuries, each Ulfbert sword bore its maker's name stamped proudly into the metal, a brand of supreme quality in an age of inconsistent iron. Historical accounts and surviving artifacts tell a consistent story: blades that were lighter, stronger, and could hold a keener edge than anything else on the battlefield. They bent without breaking and sliced through lesser armor with terrifying ease. Their contemporaries in the Islamic world, the famed Damascus steel blades, displayed a different kind of magic, their surfaces swirling with watery patterns known as damask, while possessing a legendary sharpness said to cleanly slice a falling silk scarf in mid-air. For hundreds of years after their production ceased, these swords existed as relics of a lost art. Even when the Industrial Revolution gave us precise furnaces and advanced metallurgy, attempts to recreate them fell short. The replicas looked the part, but they lacked the soul, the performance, the inexplicable toughness of the originals. This was the historical puzzle, a technological dead end that suggested the medieval smiths weren't just skilled craftsmen. They were masters of a material science we are only beginning to comprehend. The true secret of these blades wasn't merely lost in a forgotten recipe. It was locked away in a realm invisible to the naked eye, waiting within the atomic architecture of the steel itself. The journey to unlock these secrets starts not in a European forge, but in the distant mines and markets of ancient India. There, in a process that seemed closer to alchemy than industry, artisans produced the mystical raw material known as Wootz steel. These were not finished swords, but small, puck-shaped ingots of metal, prized and traded along routes stretching thousands of miles to the workshops of Damascus. To the medieval world, these ingots were a commodity of immense value, but to us, they are the first clue in a much larger mystery. Their creation was an intricate, almost ritualistic practice. Smiths would place specific types of iron ore along with carefully selected organic materials, things like particular leaves and wood chips, into a sealed clay pot called a crucible. This crucible was then heated in a charcoal furnace for hours, sometimes days, in a process we now call crucible smelting. It was a sealed, controlled environment, a tiny, superheated world where chemistry and craft intertwined. The organic matter did more than just burn. It introduced precise amounts of carbon into the molten iron, transforming it into a high-carbon steel. But as historian and metallurgist Dr. Alan Williams has detailed through his research, the magic was in the impurities. The specific ores and plant matter used introduced vanishingly small, almost undetectable traces of other elements into the mix, elements like vanadium. This was not a mistake, it was the result of a refined, generations-old recipe. In that sealed clay pot, through a process they could not possibly understand in modern terms, these smiths were performing the first step of advanced alloy science. They were creating a steel with a unique chemical signature, a DNA of metal that was perfectly primed for what would happen next in the forge. This foundational act, this alchemy of earth and fire, set the stage for an accidental discovery on the atomic scale, a hidden architecture waiting to be revealed when the ingot was finally hammered into a blade. That unique chemical signature was just the beginning of the recipe. The real transformation happened in the hands of the blacksmith, a master of physics and fire working without a single gauge or thermometer. Think of a baker making the world's most delicate pastry, not with flour and butter, but with glowing, white-hot metal. The process was called pattern welding, and it was an art of incredible patience and force. For a Damascus blade, the smith would take that small Wootz steel ingot and heat it until it was pliable, a radiant orange in the dim forge. Then, with rhythmic, precise hammer blows, they would begin to draw it out into a longer bar. This bar was then folded back upon itself, welded shut in the fire, and hammered flat again. This folding was repeated dozens, sometimes hundreds of times. Each fold was like adding a new page to a book, creating microscopic layers within the steel. But the smith didn't stop there. They would often twist these layered bars into spirals before welding them together, creating the complex, swirling grain patterns that would later etch into the legendary damask design on the finished sword surface. For the Ulfbert smith, working with their larger crucible steel blank, the process was slightly different but no less demanding. Their focus was on shaping the blank into the iconic sword form through careful hammering, a process that also served to further refine the metal's internal grain, aligning its crystalline structure like fibers in wood. The temperature was everything. A master smith judged the heat by the color of the metal alone, a shimmering cherry red for forging, a specific pale yellow for the critical quenching phase. Quenching was the moment of truth where the glowing blade was plunged into a liquid, often water or oil. This rapid cooling locked the steel's structure into an extremely hard state. But if done at the wrong temperature or angle, it could shatter the blade instantly, wasting weeks of work. This intense mechanical and thermal working did far more than shape a deadly profile. With every hammer blow and every controlled cooling, the smith was mechanically inducing stresses and creating the perfect physical conditions for something extraordinary to happen at a scale they could never see. They were building an invisible architecture layer by layer, forging a bridge between their visible craft and a hidden nanoscience waiting within the metal. For centuries, the swords remained silent, their secrets locked away behind a polished surface. Then, in the late 20th century, science finally developed the eyes to see. The key was a tool called the scanning electron microscope, a device that doesn't use light, but a focused beam of electrons to scan an object's surface, revealing details thousands of times smaller than the width of a human hair. For the first time, researchers could look beyond the beautiful damask patterns and into the metal's very soul. One of the pioneers of this work was materials scientist Dr. John Verhoeven, when his team at Iowa State University prepared a sample from a genuine Damascus blade and placed it under the microscope. They expected to see the layered structure from the folding process. What they saw instead left them speechless. As Dr. Verhoeven later described, the surface revealed not a chaotic grain, but an exquisitely ordered, intricate landscape. Etched into the steel were countless, impossibly tiny structures, perfect spheres and tubes of a super-hard material called cementite, all arranged in delicate, interconnected chains and bands. It looked less like forged metal and more like a meticulously engineered nanomaterial, a microscopic city of incredible complexity and strength. This was the empirical proof, the moment legend became science. The swirling patterns on the surface weren't just for show, they were the visible echo of this hidden, nanoscale architecture. The mystery of the swords had just deepened dramatically, shifting from a question of lost skill to a profound puzzle of atomic engineering. How did medieval blacksmiths working by eye and instinct build this invisible fortress within their steel? The answer lies in the final, most delicate step of their ancient craft. That microscopic city held a secret even more astonishing than its order. Within those etched bands of cementite, researchers discovered structures so advanced they seem ripped from a modern engineering textbook. Woven through the ancient steel were bundles of carbon nanotubes, tubes of carbon atoms arranged in perfect hexagonal lattices, each one just a few billionths of a meter wide. Alongside them ran incredibly strong, wire-like structures of cementite known as nanowires. To understand their role, picture the steel matrix as a dense forest. The carbon nanotubes are like impossibly strong, flexible vines growing between the trees, while the cementite nanowires act like microscopic steel rebar, rigid rods that reinforce the entire structure. This created a natural composite material, a perfect marriage of flexibility and immense strength on a scale the Smiths could never have conceived. So how did these nano wonders form? The answer lies in the very process we just witnessed, the cyclic hammering and controlled cooling, guided by the master smith's hand, didn't just shape the sword, it transformed the internal chemistry. The visible damask pattern you see on the surface corresponds to those bands of cementite. During the intense thermal cycling, trace impurities like vanadium, which came from those original Indian ores, acted as natural catalysts. They encouraged the carbon in the steel to reorganize under immense heat and pressure into these nanotubes and nanowires. This wasn't a single step, but a gradual, self-assembling process built over countless folds and quenches. The result was a blade with physics-defying properties. These nanostructures acted as internal reinforcements, preventing cracks from spreading, giving the steel its legendary toughness. More remarkably, they created a self-sharpening effect. As the blade was used, the softer steel around these super-hard nanowires would wear away slightly faster, leaving a microscopically serrated edge, like a natural saw, that maintained its sharpness far longer than any uniform metal could. This elegant, integrated system is what our most advanced labs struggle to copy. We can make carbon nanotubes in isolated, pristine conditions, but we cannot yet weave them seamlessly into bulk steel through the simple, beautiful violence of a hammer and forge. The medieval smiths didn't build this nano-architecture deliberately. They created the perfect conditions for the steel to build itself. While Damascus Steel built a nanoscale city within its layers, the Ulfbert Sword achieved its legendary status through a different kind of perfection, one of breathtaking purity. When researchers examined a genuine Ulfbert blade under their most powerful microscopes, they saw something almost alien compared to other European swords of the era. Instead of a chaotic, slag-filled matrix, the metal was stunningly clean and uniform. This was the result of its crucible smelting origin, a process that allowed impurities and slag, the brittle glass-like byproducts of smelting, to rise to the top of the molten metal and be removed. What remained was a steel of exceptional homogeneity, a consistent internal environment from edge to spine. At the microscopic level, this steel was composed primarily of a structure called martensite, an extremely hard arrangement of iron and carbon atoms formed by that masterful quench. The nanotechnology here wasn't about adding new structures, but about perfecting the foundation itself. It was the absence of defects, the near-total elimination of weak points at the micro and even nanoscale that made the steel so extraordinary. Think of it like a pane of glass. Ordinary medieval steel was like frosted glass, full of tiny bubbles and imperfections that scatter light and create weak spots. The Ulfbert steel, by contrast, was like optically clear, tempered glass, with a flawless, uniform structure that allows light to pass straight through and gives it incredible strength. This pristine matrix, combined with a carbon content meticulously controlled at around 1.2%, gave the blade its impossible combination of traits. It was hard enough to hold a devastating edge, yet flexible enough to bend under immense stress and spring back to true, resisting the catastrophic shattering that doomed lesser blades. For centuries after the Ulfbert workshops vanished, European smiths struggled to replicate this balance, their steel either too soft to hold an edge or too brittle to survive a battle. Even today, achieving that specific marriage of historical purity and performance with period methods remains a towering challenge, a silent testament to the Viking smiths' unintentional mastery over the invisible landscape of their metal. This hidden architecture depended on a chemical recipe no one knew they were writing. The genius of these blades wasn't just in the hammer or the heat, but in the very earth from which they were born. Modern metallurgy strives for purity, removing every last trace of anything that isn't iron or carbon. But for the medieval smith, what we call impurities were the secret sauce. Elements like vanadium, molybdenum, and even phosphorus, present in tiny amounts in their specific local ores or introduced through the leaves and woods they used in their furnaces, were not mistakes. They were accidental, essential catalysts. Think of a master chef who insists on using water from a particular spring to make their bread, unaware that the unique mineral content in that water is what perfects the dough's texture. The blacksmiths were that chef. Their tradition and relentless trial and error led them to source materials from specific locations, like the legendary mines of India for Wootz steel, because those ores simply produced a better blade. They didn't know about vanadium, but they knew that this particular rock, when treated in their specific way, yielded a metal with unparalleled strength. Scientifically, these trace elements acted as grain refiners and carbide formers. Vanadium, for instance, is a powerful grain refiner. During the intense thermal cycling of forging, it inhibits the growth of large, weak crystals in the steel. More crucially, it promotes the formation and stabilization of those super-hard cementite nanowires we saw under the microscope. It encourages the carbon in the steel to organize itself into those incredibly strong nanoscale structures rather than dispersing weakly throughout the metal. Molybdenum and chromium added toughness and wear resistance, subtly changing how the steel responded to the quench. This was accidental nano-engineering at its most profound. The smiths, through generations of refined practice, had empirically optimized a process that leveraged specific geochemistry. They created the perfect conditions for these trace elements to guide the self-assembly of carbon into a nano-reinforced composite. This formula was so delicate, so tied to a specific chain of resources and practiced ritual, that it vanished when those supply chains were disrupted or the oral traditions of the craft were lost. The secret wasn't just a technique, it was a symphony of place, material, and human intuition, playing a song we are still trying to hear. Modern steelmaking seeks to eliminate every variable, but the medieval forge thrived on beautiful chaos. The final, most dramatic step in the sword's creation was the quench, the moment the glowing blade met its liquid fate. Unlike today's precisely controlled industrial baths, the medieval smith had no digital thermometer, no climate-controlled chamber. He judged the metal's readiness by a shifting palette of color, from cherry red to a pale, luminous yellow, and then plunged it into a quenching medium whose exact nature remains part of the craft's lost lore. Historical accounts and folklore suggest a range of possibilities, from ordinary water or brine to more exotic substances like specific oils or even animal-derived liquids. The key point is not the sensationalism of the material, but its inherent unpredictability. The temperature of that liquid wasn't held constant. It fluctuated with the ambient air of the workshop, cool in the morning, warmer by afternoon. The blade itself, with its varying thickness from spine to edge, would cool at different rates, creating a complex landscape of thermal stress within the metal. To our modern engineering mindset, this is a recipe for disaster, a sure path to warping or catastrophic cracking. Yet, for these ancient blades, it may have been the essential catalyst for their nanoscale wonders. Think of it not as a flaw, but as a kind of thermodynamic dance. The uneven, uncontrolled cooling created intricate gradients of heat and stress, a dynamic environment that pushed and pulled at the steel's crystalline structure as it solidified. This very instability, this controlled chaos, could have provided the necessary energy and the specific conditions to encourage the formation of those cementite nanowires and carbon nanotubes. It's akin to how the unpredictable forces of wind and water over millennia shape a canyon's intricate layers, or how variable temperatures in the Earth's crust drive the formation of complex crystals. The smith, by embracing an imperfect, variable process, was unknowingly performing a sophisticated form of materials engineering. He was allowing the natural physics of differential cooling to guide the self-assembly of the steel's strongest possible form. This presents a profound challenge to contemporary manufacturing, where the ultimate goal is perfect, repeatable uniformity. What if, in our quest to eliminate all variables, we have also eliminated the very conditions that can give rise to the most resilient, complex internal architectures? The lesson of the quench is that sometimes the path to perfection isn't through total control, but through a masterful understanding of how to harness beneficial chaos. This process reveals a fifth, deeply sophisticated insight. The ultimate secret of these blades is not something the smiths added, but something they allowed to happen. Modern nanotechnology often works like a master watchmaker, painstakingly placing each tiny gear and spring into place from the top down. The medieval forge worked from the bottom up. By combining that specific chemical recipe from the earth with the rhythmic violence of the hammer and the unpredictable dance of the quench, the smiths did not build the nanostructures. Instead, they created the perfect, dynamic environment for the steel to organize itself. Think of a gardener preparing a perfect seedbed with the right soil, moisture, and sunlight. The gardener does not build the plant, but by understanding and providing the ideal conditions, they guide the seed to grow into its strongest, most beautiful form. The master smith was that gardener, and the steel was a living material responding to his care. The visible damask pattern on the surface is the macroscopic echo of this self-organization. It flows down through the layers of folded metal, into the microscopic bands of cementite, and finally into the atomic lattice of the carbon nanotubes themselves. This is a hierarchical structure where order emerges at every scale, from what you can see with your eye down to what you need an electron microscope to find. The philosophical implication is profound. This represents a lost wisdom of working with a material's intrinsic properties, of listening to what the metal wants to become under the right conditions, rather than forcing a rigid external design upon it. The smith's role was not as a dictator, but as a facilitator of natural law. He set the stage and then let physics and chemistry perform the miracle. Let's take a specific, tangible example to see this entire process come together. One of the most celebrated patterns in Damascus Steel is known as Mohammed's ladder, a design featuring a series of parallel, undulating bands that resemble the rungs of a ladder running the length of the blade. This is not just an etching on the surface, it is the final, visible chapter of a story written deep within the metal. To understand it, we must read that story backwards, from what the eye sees down to what the electron microscope reveals. The first step for the smith was to create the raw material for this pattern. He would begin with several small Wootz steel ingots, each with that specific chemical signature from the crucible. He would hammer and fold these ingots separately, creating individual bars with hundreds of fine layers. Then, the true artistry began. To form the ladder pattern, the smith would take these layered bars and, while they were at a critical forging heat, use special tools to create a series of deep, parallel grooves along their length. He would then twist these grooved bars in precise, alternating directions before welding them all together into the core of the blade. When this composite block was finally forged flat and shaped into a sword, those twisted, grooved layers were compressed and stretched, creating the distinctive, repeating banded pattern we recognize as Mohammed's ladder. Now, if you were to take a cross-section of that blade and look at it under a simple magnifying glass, you would see the physical layers themselves, like the grain in a piece of exotic wood. Each one of those visible bands in the pattern corresponds to a packet of these micro-layers, a region where the steel has a slightly different composition and structure due to the folding and twisting. This is where the hidden engineering takes over. When the blade was etched in mild acid, a traditional finishing step, these different layers reacted at different rates. The areas with a higher concentration of cementite nanowires resisted the acid more, appearing as bright, silvery lines. The softer steel in between etched darker, creating the stunning visual contrast. So, the beautiful rung you see is actually a topographic map of the steel's internal strength. That bright, shining line in the pattern is the surface expression of a dense, vertical band of cementite nanowires running through the steel like a microscopic reinforcing column. It is a direct one-to-one relationship. The macro beauty that collectors have admired for centuries is a perfect map of the nano-architecture that gave the sword its legendary performance. The pattern was not applied, it was grown from the inside out. Every swirl and ladder rung is a signature left by the self-assembling nanowires, proving that in these ancient forges, the highest art was an accidental byproduct of the most profound material science. This leaves us with a profound scientific conundrum. With all our advanced tools and knowledge, why can't we simply recreate these blades? The answer is not a single missing piece, but a perfect storm of lost context. The first and perhaps greatest hurdle is the earth itself. The exact ore sources used by the medieval smiths, with their unique, irreplaceable cocktail of trace elements like vanadium and molybdenum, are either lost to history or long since depleted. We can analyze a finished sword and know what's in it, but we cannot find that same geological fingerprint in a mine today. Modern metallurgy uses pure, standardized materials, but the ancient craft depended on the accidental genius of specific, impure rocks. Second, the process itself was an unrecorded symphony. While we understand the broad strokes of folding, hammering, and quenching, the precise nuances were never written down. How many folds for a specific pattern, at what exact color, judged by a specific forge's firelight, should the quench begin? What was the precise angle of the hammer blows to induce the perfect internal stress? This was tacit knowledge, passed from master to apprentice through decades of practice, a living art that died with its last practitioners. As one contemporary metallurgist put it, we are trying to reverse engineer a recipe where the instructions are written in a lost language, using ingredients that no longer exist. The third and most frustrating hurdle is at the nanoscale itself. In the lab, we can create carbon nanotubes and cementite nanowires, but when we try to synthetically introduce them into bulk steel, the results are often disappointing. The nanostructures clump together or create stress concentrations, making the metal brittle and weak. We are excellent at building these components from the top down in a sterile environment, but we cannot replicate the conditions that allowed the steel to grow them from the bottom up, seamlessly integrated during the forging process. The medieval sword is not just a piece of metal with nanostructures in it. It is a unified system where the macro, micro, and nanoscales are all perfectly aligned, each layer of complexity supporting the others. This integration creates what scientists call emergent properties, capabilities that arise from the whole system that are greater than the sum of its parts. We can copy the parts, but we cannot yet summon the emergent magic of the whole. Our attempts are technically proficient replicas, but they lack the soul and the performance of the originals, a humbling reminder that some ancient wisdom was written not in books, but in the very structure of matter. The true heart of this nano-engineering miracle was not a tool or a formula, but a human being. The master smith standing before his forge possessed a kind of knowledge that no modern textbook could ever contain. This was tacit knowledge, a deep, intuitive understanding embedded in the hands, the eyes, and the ears, refined over a lifetime at the anvil. It was learned not through lectures, but through decades of silent observation, guided practice, and the gentle, sometimes harsh, correction of a teacher. An apprentice didn't just watch his master work, he absorbed the rhythm of the hammer, learned to distinguish the subtle hiss of steel at 800 degrees from the quieter sigh at 750, and developed a feel for how the metal resisted the tongs at the precise moment it was ready for the quench. The color of the heated metal was his only thermometer, a shifting spectrum from deep cherry to pale straw yellow, each hue signaling a critical phase in the steel's transformation. The sound of a hammer strike told a story, a dull thud indicating a cold weld, a bright ring signaling proper fusion. This was the invisible software required to run the nanoscale hardware of the steel. The master was programming the material's behavior through a language of fire, force, and sensory feedback that was never written down. He held in his memory and muscle the exact sequence, the precise pressures, and the intuitive timing that coaxed the nanowires to form. This knowledge was cumulative, each generation adding its own refinements, its own hard-won insights to a living tradition. When the social and economic structures that supported these master-apprentice guilds began to fade, when wars disrupted trade routes and centralized industry replaced artisan workshops, this fragile chain of transmission was broken. The knowledge didn't vanish in a single dramatic event. It evaporated silently, one retiring master at a time, with no apprentice left to receive the final, crucial lesson. The loss was catastrophic because it was complete, the equivalent of deleting the only operating system for a supremely advanced computer. We are left with the hardware, the beautiful swords themselves, but without the software of lived experience to make them work again. This forces a haunting reflection. How many other sophisticated ancient techniques, from Roman concrete to certain lost medicinal preparations, have vanished not because they were ineffective, but because their essential wisdom resided solely in the hands and minds of practitioners who took their secrets to their final resting place. It suggests that our historical timeline of technological progress may be littered with such silent dead ends, peaks of achievement that were reached and then forgotten, leaving behind only enigmatic artifacts for us to puzzle over. This places the two technological worlds in stark contrast. On one side stands the medieval forge, a process-driven, holistic system. Its goal was singular and magnificent: to create the perfect weapon. It worked by harnessing natural self-assembly, using specific earth-born ingredients, and the controlled chaos of the forge to guide the steel into forming its own nano-reinforcements. The strength of this approach was its ability to create a locally optimized miracle, a blade whose properties emerged beautifully from the entire integrated process. Its weakness, however, was profound fragility. The knowledge was tacit and irreproducible, the material sources unique, and the output was one breathtaking artifact at a time. It was artisanal genius at its peak, but it was not a scalable technology. On the other side stands modern materials science, an analysis-driven, reductionist powerhouse. Its goal is not a single perfect sword, but the creation of scalable, uniform materials for countless applications, from skyscrapers to spacecraft. It relies on precise synthetic fabrication, building materials atom by atom in controlled environments to exact specifications. The strength here is immense control, consistency, and the ability to produce vast quantities of reliable material. We can analyze the ancient sword down to its last atom and understand, in theory, how it works. Yet the weakness in this specific challenge is integration. We struggle to replicate that elegant, bottom-up self-assembly within bulk steel. Our top-down methods of adding pre-made nanotubes often create weak interfaces and stress points. We can make a stronger general steel, but we cannot yet forge a new Damascus blade that matches the historic original's unique combination of hardness, toughness and self-sharpening grace. This is not a failure of modern science, but a revelation. It shows that the medieval swords represent the triumph of a different technological philosophy, one that viewed material, craftsman, and process as an inseparable whole. They achieved a harmony between human intuition and natural physics that our analytic, industrial mindset is still learning to appreciate. Their legacy challenges a linear view of progress, suggesting that some ancient peaks were reached by paths we have since paved over. These swords shatter a long-held myth about their own time. For generations, the popular image of the medieval era has been one of darkness, a grim parenthesis between the light of Rome and the brilliance of the Renaissance, a time of stagnation where knowledge was lost and technology stood still. But the nanotechnology hidden within these blades tells a very different story. It forces us to confront a critical question. If this was a dark age, how did its craftsmen achieve a material science we are still striving to understand? The existence of the Ulfbert and Damascus Steel is not an isolated fluke, but a gleaming data point in a much broader revision of history. Scholars now see the Middle Ages as a period of profound and quiet innovation. Look at the soaring Gothic cathedrals, their stone vaults defying gravity through architectural genius that we still model in engineering software today. Consider the intricate mechanical clocks that began to mark time in European town squares, or the advances in wind and water power that revolutionized agriculture and industry. In chemistry, alchemists in their workshops, while seeking mythical transformations, laid the practical groundwork for modern metallurgy, distillation, and pharmacology through relentless experimentation. The swords are a perfect symbol of this hidden technological vitality. They represent a pinnacle of achievement reached not in spite of the era's constraints, but through a deep mastery of them. Medieval innovators worked within their own framework, one built on observation, tradition, and a hands-on dialogue with materials. They didn't have the periodic table, but they had an empirical genius for recognizing that this ore from that valley made a better blade. They didn't have thermodynamics, but they developed an intuitive, sensory understanding of heat and stress that could guide atomic structures. This reframes the entire period. It wasn't an age waiting for the future to begin. It was an age building its own future with the tools and concepts it possessed. The term Dark Ages says more about our own historical blind spots than it does about the capabilities of the people who lived then. When we dismiss 1,000 years of human experience as a blank space, we risk missing the subtle, sophisticated ways our ancestors solved complex problems. The lesson of the swords is an invitation to look again. It asks us to re-examine other artifacts, from ancient concrete to forgotten alloys, not as primitive attempts, but as potential repositories of lost wisdom. What other quiet revolutions in craft and science are waiting to be rediscovered, hidden in plain sight within the objects our ancestors left behind? This hidden knowledge points us toward a future built on ancient wisdom. For decades, scientists have looked to nature for inspiration in a field called biomimetics, studying the structure of spider silk for stronger fibers or the lotus leaf for self-cleaning surfaces. But what if we expanded that search to include the pinnacle of human craft? We might call this new approach archeomimetics, the art of learning from the ingenious solutions our ancestors embedded in their creations. The self-assembling nanocomposite within a Damascus blade is a masterclass in resilience. Its intricate network of carbon nanotubes and cementite nanowires acts as a microscopic defense system, stopping cracks before they can spread. Imagine applying that same structural principle to the alloys used in aircraft wings or the frames of spacecraft, where a single point of failure can have grave consequences. A material that mimics this internal architecture could lead to a new generation of fracture-resistant metals, able to withstand incredible stress and fatigue, making travel safer and vehicles more durable. Similarly, the lesson of the Ulfbert is one of sublime purity. Its homogeneous, defect-free matrix represents an ideal state for any high-performance material. This ancient standard could inspire better processes for manufacturing critical tools, from surgical scalpels that need to hold a flawless edge to industrial drill bits that must resist wear under extreme pressure. By studying how those Viking smiths achieved such consistency without modern precision instruments, we might uncover more efficient, perhaps even more elegant, pathways to material perfection. The profound lesson here is that these swords are far more than relics of war or museum curiosities. They are active blueprints, repositories of solved problems. They represent millennia-old answers to questions we are still asking in our most advanced labs about strength, durability, and the elegant integration of form and function. Looking back at these artifacts with fresh eyes isn't about nostalgia. It's about recognizing that the timeline of human innovation isn't a straight, upward line. It is a spiral where brilliant ideas from the past can intersect with our present needs, offering unexpected keys to unlocking the future. Every breakthrough in understanding comes with a cost. To see the nanowires within a Damascus blade, researchers had to cut a tiny piece from it, a process called destructive sampling. This presents a profound ethical dilemma that sits at the heart of modern archaeology and materials science. On one side, you have the conservators and historians whose sacred duty is preservation. Their argument is powerful and clear. Each of these swords is a unique, non-renewable artifact, a direct physical link to a vanished world. Every nick, every patina, every microscopic scratch from its working life is part of its biography. To cut into it is to destroy a part of that story forever, reducing an object of cultural and historical significance to a mere data point. For them, the artifact in its complete, untouched state is the ultimate primary source, and our responsibility is to safeguard it for future generations who may have even better, non-invasive ways to study it. The thought of taking a saw to 1,000-year-old Ulfbert is, from this perspective, an act of vandalism, no matter how noble the scientific intent. The materials scientists, however, speak with an equally compelling voice. They argue that the true story of these objects isn't just in their shape or their surface, but locked deep within their atomic structure. Non-destructive techniques like surface imaging or X-rays can only tell us so much. To truly understand the self-assembly of the carbon nanotubes, to map the precise distribution of trace elements like vanadium, you often need to look at a cross-section. You need to place a sample inside that electron microscope. The knowledge gained isn't just academic. It can rewrite chapters of human technological history and inspire the next generation of advanced materials. From this viewpoint, a minute sample from the tang, the part of the blade hidden under the grip, is a small sacrifice for a monumental gain in human understanding. It transforms the sword from a silent relic into a teacher, actively sharing secrets that could benefit humanity for centuries to come. This tension isn't about right versus wrong. It's about two different forms of reverence, one for the object itself and one for the knowledge it contains. Fortunately, the field is evolving to bridge this divide. New, powerful non-destructive technologies are offering a middle path. One of the most promising is the use of synchrotron radiation. Imagine a facility the size of a sports stadium where electrons are accelerated to near light speed, producing incredibly intense, focused beams of X-rays. By directing this beam at an intact sword, scientists can perform a kind of high-resolution, three-dimensional scan, peering deep into the metal's internal structure without making a single cut. They can map crystallographic structures, detect variations in composition, and even infer stress patterns left by the ancient hammer. It's like developing X-ray vision for history. While not every question can be answered this way, and access to such facilities is limited, it represents a hopeful direction. It embodies a principle of minimal intervention, seeking maximum knowledge with zero physical alteration. This ethical balancing act ultimately underscores the incredible value and fragility of what we are studying. Each sword is a closed book written in the language of atoms, and we only get so many pages to read. Every analysis, destructive or not, must be considered with the utmost care, weighing the potential knowledge against the permanent loss. It forces a humble perspective on our pursuit. We are not just technicians extracting data, we are custodians of a legacy. The pursuit of their nanoscale secrets must be conducted with a deep respect for their historical wholeness. This delicate dance between knowing and preserving reminds us that these are not merely specimens, but singular witnesses to a forgotten height of human ingenuity, and we owe it to both the past and the future to listen to their stories with wisdom and with care. The story of Damascus and Ulfbert Steel is not a solitary marvel. It is a single, brilliant chapter in a much larger global story. From the islands of Japan to the courts of ancient China, cultures separated by vast oceans and millennia independently pursued the same elusive goal, the perfect blade, and in doing so, each may have brushed against the same invisible frontier of material science. Take the legendary Japanese katana, a sword as much a spiritual object as a weapon. Its soul was forged from a specialized steel called tamahagane, produced in a traditional clay furnace called a tatara. This process created a steel with varying carbon content, which the master smith would then fold and weld repeatedly, not unlike the Damascus technique. But the true magic came in the final tempering. The smith would paint the blade's spine with a special clay slurry, leaving the edge thinly coated or bare. When the glowing sword was quenched, the thinly coated edge cooled rapidly, transforming into an incredibly hard, needle-like crystalline structure called martensite. The clay-insulated spine cooled slowly, remaining softer and more flexible. This differential quenching created the katana's iconic curvature and its legendary combination of a razor-sharp edge with a shock-absorbing body. Modern analysis suggests that the martensite formed at the edge isn't just hard. It possesses a uniquely refined nanoscale grain structure, a product of that precise thermal shock controlled by the simple clay coating. Half a world away, ancient Chinese texts speak of a mythical material known as cerric iron, a steel of supposedly peerless quality traded along the Silk Road. While no definitive artifact has been conclusively identified, the persistent legends suggest Chinese metallurgists, too, had mastered advanced crucible or forging techniques that yielded a metal of extraordinary properties. The descriptions echo the praises sung of Damascus Steel, hinting at another independent branch on humanity's technological tree reaching for the same heights. This pattern reveals something profound. It wasn't a single secret passed between empires, but a universal human phenomenon. Isolated cultures, through generations of painstaking trial and error, of careful observation and refined ritual, were all independently probing the limits of their world. They were engaging in a global, uncoordinated experiment in material science, each culture using the local ores and fuels available to them, guided by their own philosophies and needs. The fact that so many converged on creating blades with near-mythical attributes suggests they were all tapping into fundamental principles of physics and metallurgy, principles we now describe with words like grain refinement, differential hardening, and nanoscale self-assembly. They just described it with the language of craft, spirit, and fire. This global pursuit of the ultimate blade speaks to a deep, shared human drive, the relentless urge to take the raw materials of the earth and transform them into an expression of both art and ultimate performance. It tells us that the quest to push matter to its absolute limit, to find the perfect harmony between strength and flexibility, is a story written not in one nation's history, but in the collective ingenuity of our species. The warrior who wielded such a blade would have known it was special, but the true reason for its superiority remained a mystery even to him. How does a society explain a tool that performs so far beyond the ordinary? When technology becomes indistinguishable from magic, legend steps in to fill the gap. Across cultures, the greatest swords were never just weapons. They were characters in their own right, endowed with souls and supernatural origins. Think of King Arthur's Excalibur, drawn from the stone, its blade gleaming with otherworldly light, or Roland's unbreakable sword, Durandal, said to contain holy relics within its hilt. In Norse sagas, swords were often named and described as having wills of their own. These are more than just exciting stories for fireside tales. They are a fascinating form of historical data. The fantastical properties ascribed to these legendary blades often map, with uncanny precision, onto the real-world performance of steels like Damascus and Ulfbert. A legend claims a sword could cleave a boulder in two. In reality, a blade with a nano-reinforced edge and incredible toughness might survive striking stone where a lesser weapon would shatter, an event so remarkable it would be retold for generations, growing more epic with each telling. A myth says a blade never lost its edge. This echoes the real, head-scratching durability and self-sharpening effect of those carbon nanotube serrations, a property that would seem perpetual to a warrior used to constantly honing his equipment. The story of a sword that could cut through any armor mirrors the battlefield reality of an Ulfbert slicing through the iron rings of chainmail. What we are seeing is a process of translation. Faced with an object that defied everyday understanding, people reached for the only vocabulary they had, the language of the supernatural and the divine. They described the effect, not the cause. The magic was a pre-scientific term for material properties like incredible fracture toughness, high wear resistance, and a resilient, sharp edge. The legend of the sword's divine forging, perhaps by elves or gods, is a narrative stand-in for the lost, incomprehensible mastery of the human smith. This interplay between technological reality and cultural narrative is where these swords achieved a kind of immortality. The physical artifact might eventually rust away or be lost, but the story, inflated and mythologized, lived on. These legends served as a folk memory, a cultural echo of a technological height that had been reached and then forgotten. They preserved the fame and the awe of these objects long after the last master who knew how to make them had passed. In a world without material science textbooks, the epic poem and the heroic saga became the archive, storing the memory of human achievement in a form that could survive centuries of social change and conflict. The magic in the story was the only container strong enough to hold the truth of the science. The perfect sword began not with a hammer, but with the land itself. Every forest, every stream, every vein of ore in the ground was an irreplaceable ingredient in a recipe written by the environment. Consider the Viking smith seeking iron. His primary source was not a deep mine, but the cold, peat-rich bogs of Scandinavia. Over centuries, iron-bearing groundwater would seep into these bogs, where bacteria would slowly precipitate the iron into a porous, rusty material known as bog iron. This ore was relatively easy to collect, but its chemical signature was unique, shaped by the specific minerals dissolved in that region's water and soil. It created a bloomery iron with its own particular blend of trace elements. Similarly, the legendary Wootz steel of India relied on specific iron sands from the Deccan Plateau, sands rich in vanadium and other trace catalysts. The smith had no control over this geological lottery. The sword's potential was literally dug from the ground, pre-loaded with a chemical destiny. The fuel source was equally critical. The intense, sustained heat required for crucible smelting or high-quality forging came from charcoal, and not just any charcoal. The type of wood used, be it oak, alder, or a specific local hardwood, affected the furnace atmosphere and could even impart minute traces of elements like potassium or phosphorus into the metal. A forest of oak trees wasn't just a source of fuel, It was an integral part of the metallurgical process. Even the quenching medium, whether it was water from a particular spring believed to be especially cold or fast-flowing, or a special oil, was a product of the immediate local environment. This created a profound form of resource determinism. The technology was not a portable set of instructions. It was an emergent property of a specific place. The master smith's knowledge was only half the equation. The other half was a precise, localized basket of natural resources. This meant the technology of the Ulfbert or Damascus blade could not be easily exported. You could kidnap a master smith and force him to work in a new land, but if the local bog iron lacked the right impurities, or if the charcoal from different trees burned at a slightly different temperature, the magic would fail. The sword was a child of its ecosystem. This intimate bond held a hidden fragility. When historical forces shifted, this delicate system collapsed. Trade routes that supplied Indian Wootz ingots to Damascus could be severed by war or political change. Centuries of harvesting specific forests for high-quality charcoal could lead to local deforestation, forcing smiths to use inferior wood that altered their results. A vital ore source could simply be exhausted, mined out after generations of use. When any one of these pillars was removed, the entire edifice of knowledge became theoretical. The smiths still knew how to work, but they no longer had the what to work with. Their refined craft was suddenly trying to play a symphony with missing instruments. This offers a sobering lens through which to view our own technological age. We pride ourselves on global supply chains and interchangeable components, but how many of our own advanced technologies depend on a similar, fragile web of specific resources? Rare earth elements for electronics, specific mineral deposits for batteries, even stable climatic conditions for agriculture, all form the modern ecosystem for our way of life. The story of these swords is a cautionary tale about sustainability. It reminds us that a technology, no matter how advanced, is not truly mastered until we understand its deepest dependencies on the natural world. A peak of human achievement can be reached and then lost not through a loss of ideas, but through a rupture in the relationship between those ideas and the earth that made them possible. To truly see the soul of the steel, we must move beyond mere microscopy and into a realm where science touches the edge of science fiction. The scanning electron microscope gave us our first breathtaking glimpse of the nanowires, but it could only show us their shape and general composition. To understand their genesis, we need to know exactly what they are made of, atom by atom, and how those atoms are arranged in three-dimensional space. This is the promise of a revolutionary tool called atom probe tomography. Imagine holding a needle made of the very material you wish to study, a fragment so small it tapers to a point just a few hundred atoms wide. This needle is placed inside a vacuum chamber and cooled to near absolute zero. Then, an incredibly precise pulse of energy, either a laser or an electric voltage, is applied, causing atoms at the very tip to ionize one by one. These ionized atoms are then hurled toward a detector that records their time of flight, which tells us their mass, and their impact position, which tells us exactly where they came from in the original sample. By repeating this process millions of times, stripping the material away atom by atom, the instrument builds a staggeringly detailed three-dimensional map. It is a kind of atomic archaeology, disassembling a structure to catalog every single brick. For a Damascus Steel nanowire, atom probe tomography could, in theory, provide the ultimate blueprint. It could show us not just that the wire is made of cementite, but the precise location of every iron and carbon atom within its crystal lattice. It could map the exact positions of those critical trace elements like vanadium, revealing whether they sit at the boundaries between crystals, acting as guides for the nanowire's growth, or are woven into the structure itself. For an Ulfbert blade, it could create a perfect digital model of that pristine steel matrix, showing the distribution of carbon and any residual elements with atomic precision. This data would be the closest thing we could ever get to a complete recipe, a parts list for the universe's most resilient steel. The potential is dizzying. With such a map, materials scientists could run ultra-high-fidelity computer simulations to understand exactly how stress flows through this atomic architecture, or how a crack is arrested by a single, perfectly placed nanotube. It offers a path to reverse engineering not just the material, but the very physics of its performance. Yet, this atomic map presents us with a profound philosophical puzzle. Knowing the what in perfect detail does not automatically grant us the how of its creation. It is like being given a photograph of a magnificent, finished cathedral, with every stone and stained glass window meticulously documented. The photograph tells you what the cathedral is, but it reveals nothing of the centuries of craft, the scaffolding, the crane designs, the mason's intuitive sense for balance, or the specific sequence in which the arches were raised. The atomic map is the cathedral's photograph. The medieval forge, with its rhythmic hammering and sensory quench, was the living, dynamic process of construction. Even if we had a perfect atomic blueprint, could we use it to guide a modern industrial process to assemble atoms in exactly the same way? Our manufacturing excels at top-down control, at imposing order. The ancient method was about creating conditions for bottom-up self-assembly, for allowing order to emerge. This is the core challenge that atom probe tomography underscores. It can show us the destination with unimaginable clarity, but the journey, the lost art of the path itself, remains the true secret locked within the blade. This distinction reveals a philosophical divide at the heart of every attempt to recreate these swords. We are not merely trying to copy an object, we are trying to resurrect an entire technological world. On one hand, we have the goal of artifact replication, using modern powder metallurgy, where ultra-fine, pure metal powders are fused under heat and pressure. We can produce a steel bar with a chemical composition nearly identical to an Ulfbert. Through computer-controlled machining and heat treatment, we can shape it into a sword that looks perfect, feels right in the hand, and performs admirably in tests. It is a faithful physical duplicate, a stunning tribute to historical design. But this is a different technological path altogether. It is a shortcut, a top-down imposition of form using 21st century tools to mimic an 11th century outcome. The blade may be a convincing twin, but it was born of a different universe of knowledge. The true and far more elusive goal is process replication. This isn't about the destination, it's about the journey. It means starting with raw, impure ore from a specific source, smelting it in a charcoal-fueled clay furnace, working the resulting bloom or ingot with hand hammers, judging temperatures by color alone, and quenching in an uncertain medium, all while aiming for that invisible nano-architecture. This path is messy, unpredictable, and deeply human. It is the authentic historical process that we seek to walk again, not because it is efficient, but because it is the only way to truly understand the achievement. The difference is profound. One approach gives us a beautiful prop, a static end product. The other offers a living dialogue with the material, a rediscovery of the chain of decisions, accidents, and intuitions that led to the miracle. When we succeed at artifact replication, we have made a copy. If we could ever succeed at process replication, we would have regained a lost language. This elevates the swords from being mere objects in a museum case. They are not the technology itself, they are the final, frozen expression of it. They are the output of a complete, integrated system that stretched from the geology of a specific hillside to the muscle memory in a master smith's arm, a system that processed natural chaos into exquisite atomic order. That system, that holistic way of knowing and making, is the true lost achievement. We can admire the magnificent cathedral, but we have forgotten how to build the scaffolding, mix the mortar, and train the masons in the old way. The sword is the proof the cathedral was built, but the builders and their art have vanished. Our modern replicas are like constructing a Gothic facade with steel beams and concrete. It may look the part, but the soul of the original construction is absent. This is why the quest continues, not just for a sharper blade, but for a deeper connection to a form of intelligence written in fire and iron. A time capsule is meant to preserve the essence of an era, but these swords do something far more profound. They capture not just objects but a living intelligence. The atomic lattice of a Damascus blade is not a random arrangement. It is a frozen moment of decision, a physical record of 1,000 tiny choices made by a master smith a millennium ago. Every hammer blow that stressed the metal, every judgment of heat by the color of the forge's glow, every instinctive pause before the quench, all of these human actions left their permanent signature in the steel's nanostructure. When we peer at those carbon nanotubes through a modern microscope, we are not just looking at ancient material, we are reading the final, tangible output of a master artisan's lifetime of learning. The sword is his ultimate manuscript, written not in ink that can fade, but in atoms that have endured. It is a direct, unbroken physical link to a mind that worked in fire and intuition, a mind that understood material behavior on a level we are still struggling to translate into our language of equations and formulas. This transforms the sword from a relic of conflict into a vessel of communication. The smith could not write a treatise on nucleation sites or stress-induced phase transformation, but he could make a blade that demonstrates those principles perfectly. His knowledge was encoded in action, and the resulting object is the stored data. Our scientific analysis is the decoding process. In this light, the laboratory becomes a strange kind of meeting place. The materials scientist with her atom probe is, in a very real sense, having a conversation across 1,000 years. She asks a question by taking a measurement, and the sword answers by revealing the structure the smith built. He communicates through the elegance of his solution, the flawless integration of nanowires that stop cracks, the homogeneous matrix that balances hardness and flex. We receive his message not in words but in performance, in the enduring proof of what his hands could achieve. This makes these artifacts the most durable time capsules imaginable. They preserve something far more fragile than cloth or parchment. They preserve applied genius. They hold the accumulated experience of generations, the refined intuition of a craft at its peak, all crystallized into a form that can still speak to us today. To study them is to listen to that quiet, persistent voice from the past, a voice that challenges our assumptions about progress and reminds us of the profound depths of human understanding that can be achieved through observation, patience, and a deep dialogue with the natural world. The true measure of a technology's impact is written not only in its performance, but in the legacy it leaves behind. Today, a genuine Ulfbert or Damascus sword is far more than a historical curiosity. It is a treasure of almost unimaginable worth. When one of these blades appears at a prestigious auction house, it commands a price that can rival a masterpiece of Renaissance painting, often selling for hundreds of thousands, even millions of dollars. This staggering financial value is a direct reflection of the composite mystique we have been exploring. Collectors are not bidding on a mere piece of old metal. They are investing in a singular artifact that represents the pinnacle of history, art, myth, and confirmed scientific wonder. Each sword is a unique nexus where all these threads converge, making it irreplaceable. In the hushed halls of the world's great museums, from the British Museum to the Metropolitan Museum of Art, these swords are not displayed alongside common weaponry. They are presented as centerpieces, often in their own dedicated cases with special lighting and detailed placards that speak of their legendary status. They are anchors for entire exhibits on medieval life or metallurgical history, drawing visitors who come to stand in quiet awe before the tangible proof of a lost genius. This cultural reverence extends powerfully into the present day. For modern Viking heritage societies and historical reenactors across Scandinavia and beyond, the Ulfbert is not just a sword, it is a symbol of ancestral ingenuity, a point of immense pride, and a direct link to a sophisticated technological identity that contradicts the old barbarian stereotypes. In the Middle East, the Damascus blade holds a similar, profound place in cultural memory. It is celebrated in poetry, art, and national identity as a testament to a golden age of Islamic science and craft, a reminder of a time when the region's workshops were at the very forefront of global innovation. This enduring significance creates a value equation that no modern replica, no matter how expertly made, can ever solve. A contemporary sword might be functionally excellent, but it lacks the depth of story, the weight of centuries, and the confirmed nanoscale secrets that make the original utterly unique. The simple, humbling fact remains: a sword forged 1,000 years ago in a charcoal-fired forge is now more valuable, more studied, and more culturally resonant than any mass-produced modern blade. Its worth is the final, definitive proof of the technology's power, a price tag placed by history itself on an achievement we can see, analyze, and admire, but still cannot fully rebuild. The path forward is not a solitary quest for a lone scientist in a lab. Unlocking the full secret of these blades demands a new kind of endeavor, one that bridges the deepest chasms between disciplines. Imagine a round table where a historian's knowledge of medieval trade routes informs a geochemist's search for ore samples, where a materials scientist's atomic map is interpreted by a master blacksmith who feels the steel's resistance in his hands. This is the collaborative model we need, a concerted effort that treats the ancient sword not as an artifact for one field, but as a complex puzzle requiring every key we possess. We must launch large-scale, well-funded research initiatives designed from the ground up for this synthesis. On one side, teams would employ the latest non-destructive technologies, like synchrotron scanning, to build a vast digital library of internal structures from dozens of authentic blades, searching for common patterns and hidden variables. Simultaneously, experimental archaeologists and traditional smiths would work in reconstructed forges, using historically sourced materials to attempt process replication, guided by the data from those scans. Each failed attempt, each blade that shatters in the quench or lacks the legendary edge, is not a defeat but a critical data point. It tells the scientists what variable might be missing from their model, perhaps a trace element they overlooked or a thermal gradient they miscalculated. This creates a powerful feedback loop. The science informs the craft, suggesting a tweak to the hammering sequence or the quenching medium. Then, the craft challenges the science, producing a physical result that either validates or refutes the latest theory. It is a dialogue between the quantitative and the qualitative, between numbers on a screen and the intuitive wisdom of the hand. The ultimate breakthrough may not come from a single eureka, a moment in a laboratory, but from the slow, patient convergence of these different ways of knowing. The collaborative model itself, this new language forged between historian and engineer, could become the most valuable legacy of the entire pursuit, a blueprint for rediscovering other lost technologies and reminding us that the greatest human puzzles are rarely solved by one mind alone. That final collaborative model points toward a deeper truth, one that reaches far beyond the walls of any laboratory or museum. The story of these swords in its entirety delivers a profound and humbling lesson about the very nature of human knowledge. In an age where we can sequence genomes, simulate universes, and instantly access the cumulative information of our species, it is a startling realization that our most sophisticated tools cannot yet rebuild what a medieval artisan created by firelight and intuition. This is not a failure of modern science, but a necessary correction to a long-held assumption. We have often viewed history, especially technological history, as a simple, linear climb. We picture a timeline where each generation stands on the shoulders of the last, ascending steadily from primitive tools to advanced machinery. The narrative is one of inevitable, cumulative progress. The Damascus and Ulfbert Sword stand as silent, magnificent counterpoints to that comforting story. They are not steps on a staircase we have since climbed past. They are distant peaks on a vast and complex landscape, summits reached by paths that have since grown over and faded from memory. Their existence forces us to replace the idea of a straight line with a more honest map, one of a rugged terrain full of towering achievements, deep valleys of forgotten understanding, and plateaus where knowledge simply held its ground for centuries. This is a landscape where capability is not a guaranteed possession, but a temporary residence. A society can gain a profound mastery, as the Smiths did over the self-assembly of steel, and then, through a combination of social change, resource depletion, or the fragility of oral tradition, that mastery can simply vanish. The knowledge isn't stolen or destroyed in a cataclysm. It evaporates, leaving behind only the breathtaking artifacts as proof it ever existed at all. This reframes our entire relationship with the past. It asks for a humility that is often absent in our technological triumphalism. To look at a 1,000-year-old sword and admit we cannot make its equal with our billion-dollar equipment is an act of intellectual honesty. It compels a deep respect for pre-industrial knowledge systems not as primitive precursors, but as sophisticated, integrated ways of understanding the world that achieved different, and in some cases unsurpassed, ends. These systems worked in harmony with local environments, relied on refined sensory observation, and encoded wisdom in practice rather than theory. They were not inferior, they were simply different, and in their specific domains, they reached heights we have not remastered. The lesson is a caution against the arrogance of assuming our current position is always the highest point on the map. It encourages a more nuanced, less condescending view of history, where we look for the peaks as well as the slopes. What other ancient technologies, from Roman concrete that self-heals to certain lost medicinal preparations, represent similar unconquered summits? The swords teach us that the journey of human ingenuity is not a relentless march forward, but an ongoing exploration of a vast and mysterious territory. Some paths lead to lasting highways, others to breathtaking vistas that are later lost to the mist. Recognizing this does not diminish our modern achievements, but it enriches our understanding of the human journey, reminding us that brilliance is not the sole property of the present, and that some echoes from the past still hold secrets we have yet to fully hear. The secret of these blades does not rest in a single, lost ingredient. It is a trinity, a threefold lock that has kept their full truth sealed for 1,000 years. The first key is the material recipe, a formula written in the language of the earth itself. This was not a simple list of elements, but a precise, irreplaceable combination of specific ores and organic additives, each from a distinct location now lost to us. The vanadium-rich sands of India, the particular bog iron of a Scandinavian peatland, the leaves and woods chosen for the charcoal, these were not interchangeable components. They formed a unique chemical signature, a geological fingerprint that acted as the catalyst for everything that followed. We can analyze a finished sword and know what is in it, but we cannot find that exact same blend in nature today. The second key is the most human element, the unrecoverable tacit knowledge of the master smith. This was the living software, the sensory-guided intuition built over a lifetime. It was the ability to judge a critical forging temperature by a precise shade of yellow in the firelight, to hear the correct ring of a hammer strike, to feel the moment the steel was ready for its fateful quench. This knowledge was never written in a manual. It was embedded in muscle memory and refined perception, passed silently from teacher to apprentice in a chain that was eventually broken. We can describe the steps, but we cannot download the instinct. The third and final key is the system itself, the holistic, self-organizing process where chemistry, thermodynamics and mechanics danced together in the forge. This was not a series of disconnected steps, but a unified, dynamic event. The specific chemistry of the ore met the rhythmic violence of the hammer, which created internal stresses that guided the formation of nanostructures during the unpredictable chaos of the quench. Each part fed into the next in a closed loop of cause and effect that modern, reductionist science struggles to model in its entirety. We excel at isolating and studying each variable, but we have not yet learned to perfectly replicate their spontaneous, synergistic conversation. Material, maker, and method, these three were fused into one object, each element dependent on the others. We can attempt to copy the material with modern alloys, we can emulate the method with advanced machinery, and we can apply immense skill as modern smiths. Yet without that original trinity, that complete, integrated system born of a specific place, person, and process, we are left with a brilliant homage, not a true resurrection. The swords stand as a testament to a form of knowledge that was not just known but lived and felt, a harmony between human intuition and the hidden laws of matter that we are still learning to hear. The final, gleaming truth of these blades is not a formula we can write down. It is a reminder that human brilliance can be crystallized in fire and forgotten in time. We stand today with electron microscopes and atomic probes, able to map every nanometer of their structure, yet still humbled by the integrated wisdom that created them. These swords are not relics of a darker age, but luminous artifacts from a sophisticated one. They prove that profound technological insight can flourish outside of laboratories and textbooks, born from generations of patient hands and watchful eyes. The carbon nanotubes and cementite nanowires woven into their steel are more than ancient engineering, they are a message. They speak of a deep, intuitive conversation between the maker and the material, a dialogue where the smith learned to listen to what the metal itself wanted to become. This was a science practiced in the rhythm of the hammer and the color of the heat, a knowledge felt in the bones and passed on in silence. Modern science continues its diligent work, and perhaps one day we will fully reconstruct the process, molecule by molecule. But for now, a part of the secret remains gracefully out of reach, locked within the very atoms of the past. This is not a failure of our present, but a gift from history. It challenges the linear story of progress and asks us to view the artifacts around us with new eyes. The next time you see an ancient tool, a piece of pottery, or a fragment of architecture, remember the lesson of the sword. Do not see only simplicity, look deeper. Within the craftsmanship of our ancestors may lie elegant solutions, sophisticated understandings of the natural world that we have yet to rediscover. Their legacy invites a quiet curiosity, a willingness to question what we think we know about the journey of human ingenuity. If this exploration into the hidden heart of history resonated with you, consider subscribing for more journeys into the forgotten corners of our past. And we would love to hear your thoughts. What other ancient creations do you believe might hold similar, untold secrets?